I will tell you about speeding up debugging for embedded. But before we can dive in, we need some setup. And that's what this video is about. When you're debugging embedded systems, you absolutely need debug symbols. Think of debug symbols as the human-readable layer of your binary. They turn raw machine code into things we can actually understand, like function names, variable names, and specific line numbers. Now this brings us to problem number one. Where on earth are your debug symbols? First, for your own application, always ensure you're compiling the -G flag. If you're using a build system like Yocto, double check that those symbols aren't being stripped away in a later step. To prevent this, use the Yocto variable inhibit package strip equals 1 in your recipe, and your executables will have debug symbols left in. And for libraries, they should be in your SDK, but they are often hidden. Let me show you what I mean. Here I am in a typical SDK for cross-compiling to an embedded target. If you look in userlib, you see the libraries. But if you run the file command on them, you will find that they are stripped. So they do not contain the debug info. The debug info is missing. So where is it? In many modern SDKs, there's a hidden folder called .debug. ls.debug. Here it is. And if you look inside this one, you'll find the unstripped heavy-duty versions of those libraries that were just missing the debug symbols. This split debug concept is very common in Yocto, so if you think you're missing your symbols, always check that hidden .debug folder. To work with these, keep two tools in your back pocket. First, we've already seen the file command. Use it to check if a binary has debug info and if it's split or combined with the debug symbols. So we can use the file command and we will see that this library is actually stripped. Then, second, the eu-strip and eu-unstrip commands from the elfutils package help you combine or split apart debug symbols again. So we could use eu-strip to strip away the debug information from libqt6 core here to make it more lightweight. Or we could use eu-unstrip to combine the library with missing debug information with the debug information that comes from that secret debug folder. And if we do that, we will see that we actually get a library that has the information inside. Now here's the second major problem when debugging. Debug symbols are huge. We're talking gigabytes here. If you're working on an embedded device with limited storage, you can't just copy everything over. So how do we handle this? I have three solutions for you. Solution one is partial debugging. Only bring over the symbols for the specific application you're working on and skip the external libraries. Yes, you will miss some debug symbols, but if you are looking for a crash in your application, the exact line number of libc or something might not be relevant for you. Solution two is to use an external USB drive. If the internal flash is full, just plug in more storage. You'll just need to tell your debugger where to find the symbols on that external path. Use the command set debug file directory to that USB drive to achieve this. If the build numbers match, GDB will pick up the symbols for you in that location. Solution 3, and this is my favorite, is remote debugging. Keep your large debug symbols on your host machine where you have plenty of disk space, but run the binary on the target using GDBserver. And keep the heavy lifting, symbol-rich GDB instance right here on your laptop. To achieve this, I need to start GDBserver on my embedded device here. For this, I run the command GDBserver --multi and provide a port, which I just call 1234 here. This allows us to connect to this device from this laptop to debug it. Back on my laptop, I will start GDB. In GDB, I need to set up the remote device. For this, there's the command target extended remote. and I can specify the IP address of this device. Also, I need to provide a port, and we set this to 1234. If this works, you will see this print out, remote debugging, using this IP address and that port. Next, I need to say what I want to start on my device. I do this with the set remote exec file command. And I say I want to start the application which is inside the root directory and which is called app-qt. Okay, also accepted that. Now I can hit run. And to see something on the screen, I actually also need to provide a platform here, which is, in this case, Linux frame buffer. And now we will see that some of the symbols will be downloaded from the target, some of the symbols will be used from the laptop, and I will end up in a situation where I can actually debug from my laptop on this device with all the symbols that I need inside my debugger. So I hit yes, and now it downloads the symbols. Once the symbols are loaded, you see the app starts up on the screen, and I'm actually inside the application and can debug it. So I can just stop the application here and get a backtrace, for example. You see, this is now the backtrace that we got from this remote target, joining all the debug information, and you see all the frames actually have names and function names attached to it. So this is a complete setup. This remote setup is what works best for me for remote debugging. And that's it. Once you have that remote connection set up, you're ready to debug efficiently without cluttering up your embedded hardware. Thanks for watching, and stay tuned for the next part where we dive in even deeper into embedded debugging. Auf Wiedersehen and goodbye.